Hello chemistry students and chemistry lovers. In this video we're gonna do chemistry titration. This is my information, the code information. Let's get into the video. Firstly, starting with personal protective equipments like gloves required, safety glasses, closed shoes and lab coat. Let's start with our setup. Make sure to clean your burette and all the glasswares with ionized distilled water, which will ensure that all the impurities are removed from your glasswares. Hence, it will be very beneficial in terms of a positive and clean result. Make sure to wash your tips too. Let down the ionized distilled water run through the tap. Always ensure the close end of your burette is pointed toward the sink but not any person. After washing with ionized distilled water, we gonna wash our burette with iodine solution. It is important to wash your burettes with the solution it has to contain. So in my case, in this titration I'm using iodine solution, so hence I have to wash my burette with iodine solution. Make sure you don't waste any chemicals. In our case we had a limited chemicals available, hence I had to close my tap and carefully uh, fill my burette with some iodine solution, which is enough for me to wash my burette. The open point of the burette was tilted towards the sink, making sure I don't spill any. It was twisted and swelled up until it went up to 0, and all the sides, all the walls are cleaned with iodine. After which I took one beaker and let my tap open so that the iodine solution washes out my tip too. This is my burette setup with iodine solution. So let's start with our first titration, which is with tomatoes. Moving on to the introduction on vitamin C titration in tomato. Iodine titration is a method for determining the concentration of vitamin C, which is ascorbic acid, in a sample. It involves a redox reaction where vitamin C reduces iodine, and the endpoint is indicated by the color of a starch iodine complex. The amount of iodine used to reach this endpoint is then used to calculate the vitamin C concentration. Fresh tomato was blended and it was made into pulp, which was then strained to be sure of we get liquidy part only. It is recommended to use a fresh tomato or blend it just before you are gonna start with your titration. With our tomato juice we gonna add HCl, which would be of 5 drops, 10 drops of 2% starch solution, and not forgetting 10 ml of water. Let's start with our main titration. Make sure your clumps and everything, your burette is on this exact normal height, that is easier for you to titrate, as well as uh, use of flask, like remove your flask and swirl if you want. Make sure to go drop by drop as you like, and keep on swirling, don't forget, until you get a persistent color. This tomato titration was done 3 more times. The same processes were repeated over and over again for 3 more times to get 4 data for my first titration on tomatoes. Let's do our calculation on this titration. Let's get started with our first calculation, which is on tomato juice, as in it was our first titration for vitamin C. So in our first titration we did four titrations, which we got 2.5 of the volume, 1.2, 1.5 and 1.3. Using these four, we're gonna calculate our mean. So let's see. Let's start with our calculations. Mean is equals to 2.5 plus 1.2 plus 1.5 plus 1.3, which is divided by 4. It will come up to 1.625 ml, and this in liters will be 0.001625 liters. We're gonna use this amount to calculate our moles of ascorbic acid, but firstly, before that, let's see our iodine molarity. So our iodine molarity is equal to C is equals to 0.01 mole per liter. This is our iodine molarity and this is our mean value. So let's note it down first. Mean was 0.001625 and iodine molarity C is equals to 0.01 mole per. So our mean is done, our iodine molarity is done. So moving on, we're gonna calculate the moles of ascorbic acid. For moles of ascorbic acid, the formula of this is concentration times volume. So moles is equals to CV, which is concentration is multiplied to volume. So it is equal to 0.01. As we found out, the iodine molarity is 0.01, so the concentration 0.01, which is multiplied by 0.001625, we get our moles of ascorbic acid, which is 1.625 times 10 to the power 5 moles. Please don't forget your units, it's important. And this is our moles of ascorbic acid. So using these moles, now we're gonna calculate our mass. So this is noted down, so let's do mass. Mass of ascorbic acid. Now calculating mass of ascorbic acid, our moles was 1.625 times 10 to the power negative 5. So mass is equals to 1.625 times 10 to the power 5. This is multiplied by 176, which is our MR. So you'll end up getting 0.00286 gram, which is 2.86 mg. So this was our moles of ascorbic acid, and this is our mass of ascorbic acid. So ascorbic acid, as you all know, it's also vitamin C. Either you say ascorbic acid or vitamin C, but vitamin C is always written in mg, so this is the final answer. If you feel like you don't understand any part or something, you can rewatch it, and you can pause your video and see my formula and everything, the calculation steps. It is in steps, easier for the understanding. So this is done. Let's start with titration 2, which is basically with orange juice. Seeing on introduction to the vitamin C titration experiment, ever wonder how much vitamin C is really in your orange juice? We can find out. This experiment uses a clever trick called titration to measure the amount of vitamin C in a sample of orange juice. We'll use iodine, a special solution, and a starch indicator to pinpoint exactly when all the vitamin C has been used up. It's like a chemical race where we watch the vitamin C get caught by the iodine, and the starch helps to indicate the color change. The burette was set up with iodine solution, and 3 molar of HCl was added of 5 drops. Make sure you are using different droppers for both the solutions. Starch solution was added, which was for 10 drops. Before adding starch and HCl, I had added 10 ml of distillated water. Sorry, I forgot to mention that. I don't know why, but I like giving a small little swirl to it before using the titration with iodine. Always adjust your burette to a good height where you can titrate as well as swirl your flask easily. Make sure to go drop by drop in case you might overshoot in accident, whereby in this experiment I end up going over. Hence I was told to change my volume of overall orange juice with HCl and also starch solution. I started up with the new solution of 50 ml orange juice, 15 ml of water and 15 drops of HCl with 5 drops of starch. Please do ensure with the orange juice, whichever orange juice you are using, and if it has extra added vitamin C in it. For mine, I guess it did, so it got overshot very easily. Keep on noting your variables to calculate the used volume of iodine solution. It will be essential in our calculations at the end. This time I made sure to go drop by drop. I did got the right color for that one, so starting with another one, I use the same volume, same HCl, same number drop of starch and also the water. I repeated the same experiment over 3 times again. Let's do the vitamin C calculation. Okay, so it's time for our calculation for this titration, which is on orange juice. So in this we did 3 titrations. Our use volume was 0.3 for the first one, 0.2 second one, and 0.2 again for the third one. Using this we gonna calculate mean. So mean is equals to 0.3 plus 0.2 plus 0.2, which is divided by 3. Either you can add the numerator first and do the dividing part later, or you can just press it directly in your calculators. You will get 0.233, which is in ml, but in liters it will be 0.00023 liters. We're gonna use this amount to calculate our moles of iodine, and then the amount we get in moles of iodine, we're gonna calculate our mass of ascorbic acid with that. So moving on, using this, we're gonna calculate our moles first. Before going on to moles, we have to know our iodine molarity concentration. So for iodine molarity, is C is equals to 0.01 mole per liter. This is our iodine molarity. So using our previous mean value, liter value, and this molarity, we're gonna calculate our moles. So moles equals to moles is C times B, which will be 0.01 mole multiplied by 0.000233, where you will get 2.33 times 10 to the power negative 6 mole. This is our moles of iodine. This is our calculation for moles of iodine solution, which is 2.33 times 10 to the power negative 6. Using that, we're gonna calculate our mass of ascorbic acid. For mass is equals to mole times mass. Our mole was 2.33 times 10 to 6 times 6. So this is our final mass of ascorbic acid. This is our final answer. Let's start with our titration 3, which is basically with apples. It is cut into pieces and ready for blending. Let's see the introduction for a vitamin C titration. Experiment using iodine and starch in apple juice. Iodine is special solution and a starch indicator used to precisely measure the vitamin C content. The starch will help us see when the vitamin C is all used up by the iodine. This was the blended juice of apple. It was blended and then strained to remove the pulpy part and just to obtain the liquidy part. Make sure to cover your stored apple juice properly, otherwise the vitamin C will get oxidized with the oxygen. In this experiment, I had taken 10 ml of apple juice as shown, pipette into the flask. Now 20 ml of water will be pipetted into the flask. Please note that I am still using the ionized distillate water for all the titrations. Now I'm adding 2% of starch solution, which would be 10 drops. After which it's 10 for HCl. For HCl I'll be adding only 5 drops. Always go drop by drop to be safe on side and to avoid overshot. Keep on swirling as you add your iodine solution drop by drop. I already had a light color change in that in just by a couple of drops, as you saw. And then the same experiments, same volumes were reused, and the experiment was repeated for 3 more times. Now let's do the vitamin C calculation. So let's look at into titration calculation for apple ascorbic acid, which is vitamin C. So for apple titration we actually did four experiments, and from that 4 we'll use 1, 2 and 4. We won't use titration 3 because that one was overshot, so we would ignore that one. So for number 1 we had 0.7 used ml, and second one was 0.6, and then fourth one was 0.1. So using these values we're gonna calculate mean. So for mean calculation we're gonna use mean. We're gonna use 0.7, 0.6 and 0.1. So for mean it is equals to 0.7 plus 0.6 plus 0.1, which is divided by 3, where you will get 0.467 mole. Shut down. So moving on to mean calculation. Mean is equals to those 3 values which will use, except for the value 3. So first was 0.7, second was 0.6, and fourth number which we're gonna use is 0.1. We're gonna ignore the third one, so it's divided by 3, which is equal to 0.467 ml, which will be 0.000467 L. So we're gonna use this volume, this amount, to calculate our mass of ascorbic acid, moles of ascorbic acid. So let's start with our moles. So in moles of ascorbic acid, moles is equals to concentration, which is 0.01, times volume, which was 0.000467. So you can do this in your calculator directly. You'll get 4.67 times 10 to the power negative 6 mole. So this is our moles of ascorbic acid. We're gonna use this to calculate mass. So moving on to the mass calculation, mass is equals to the moles times mR, which is moles times, let me write it, mR. So moles was 4.67 times 10 to the power -6, and mR, which is 176, you will get 0.0000822 gram, which would be 0.822 mg. So this is our final calculation mass. This is mass of vitamin C, which we got in apple. So this is our final answer. Now let's see the chemical significance of vitamin C. Vitamin C is volatile water-soluble antioxidant found in various fruits and vegetables. It plays a crucial biochemical role in collagen synthesis, wound healing, immune system support, and enhancing the absorption of non-human iron from plant-based foods. Moving on, ascorbic acid functions as a reducing agent, readily undergoing oxidation in redox reactions, a property that allows for its quantification through iodine titration. Its presence in goods like tomatoes, oranges, and apples contribute to their nutritional value and helps protect cells from oxidative damage. Let's go on to the observations. In all the three experiments, the redox titration technique using iodine as a titrant and starch as an endpoint indicator was effective in estimating ascorbic acid content. While orange juice showed the lowest titration volumes, likely due to either low concentration or scale limitations, the titration of tomato juice yielded more consistent results with clear endpoint transitions. Apple juice required careful observations due to overshooting in one trial, but generally showed a modest vitamin C level. Variability in data could be attributed to visual limitations in endpoint detection and manual pipetting. Nevertheless, the results across all samples demonstrated the practical application of redox chemistry for nutrient analysis and highlighted the nutritional variability among different fruit types. Now at the end, let's move to our conclusion. The titration experiments successfully demonstrated the effectiveness of iodine starch redox titration in quantifying vitamin C content in orange, tomato, and apple juices. Despite some experimental challenges like endpoint visibility and slight measurement inconsistencies, each test provided valuable insights into the ascorbic acid levels present in these fruits. These findings reinforce the importance of fruits in the human diet as source of essential vitamins and show how basic chemical techniques can be used to evaluate nutritional quality. Finally, we have came to the end of this video. Thanks for watching. Bye bye.